I hear your voice. Hey, everybody. My name's Ziggy. I'm the 75 ohm ham, and I haven't taken this apart yet, but I'm gonna. I don't care who watches me. I will wait for one person just to entertain the idea of this whole concept. Magical Mike just got this for me. He didn't get it for me. He wasn't using it. And I said I wanted to use it, but first I'm going to take it apart. But I haven't opened it yet. So this is a 1-to-1 Balun. We assume it's going to be a true Balun, and that's kind of like a whole series that I want to talk about is true Baluns versus really just, chokes and then improper chokes thereof. So it's well mounted in there. I can only just feel it vibrating on whatever its mount is. I love this box. This is a very UK box. Hey, there's one person. All right, let's open it up. I was waiting on somebody to join before I opened it up. I said it kind of be silly to open it up when nobody's watching, but I've got somebody watching. That's all I need. This is a 1-to-1 Balun that came from Magical Mike's house. KO4 PDI. What is it? Ham radio fun with KO4 PDI. Wow. Really twerked that one in there. I want to see if this is really a Balun or if this is a what I'm calling. Hey, Colin. If this is what I'm calling a and I'll tell you how I spell that. So we got Balun, or we've got Bal, not really a Balun, not really a choke, kind of something in between. How you doing today, Colin? What you getting into? This should probably pop right apart. Oh, well, here we go. So, I wonder what this paint was all about. Just hit it with some paint, boys. So, in the classical sense, this would be a Balun. However, this wrapping style is atrocious, fellas. I mean, give a damn. There's got to be, I don't know. I could never have this much hanging off the core like this. There's going to be so much leakage just from using this. Turn-wise, we've got... Oh, there's 4 people. Hey, guys. I wish I could do something with the lighting here. This is really terrible. I feel like I'm doing an injustice for everybody. Maybe I can just bring the camera closer. Oh, that's the... One day I'll be able to afford a better camera, right, guys? Hey, Hollywood, how's it going? Let's see here. Ta-da. I hear your voice. I want to hear Hollywood's voice. Here, Hollywood. There's a link. So, rap wise, we've got 1, 2. These crossovers, I don't care who you're talking to, they don't count. I've seen somebody already debunk this. You can't really induce any kind of magnetism by crossing it directly in the center here. Somebody also said mathematically it counts as like 0.2 of a turn, but that's if everything's perfect. Hey, Marvin, how's it going? Let's see. 1, 2, 3. I can't count this. 1, 2, 3, 4 wraps. What on earth is 4 wraps? 8 people. That's nice. Is it going to do some kind of balancing? Yeah, maybe. I wonder how much this product costs. I really kind of want to talk about the chart, the choke chart, though. I call it the choke chart. And my computer's going to know exactly what I'm talking to. GT3XQ. Hey, there's Hollywood. How you doing?
I'm doing okay. How about you?
Good. There's no echo, is there?
No echo at all. How do I sound?
You 10 out of 10.
Oh, good.
Yeah. So I went over to Magical Mike's earlier today.
Okay.
And I picked up some desks, and I saw this sitting out in his garage, and I've had an eyeball on it for a little bit, and I was like, I must know, for no other reason because they put the magic word on there, right?
Mm-hmm.
Yeah. So how did they do it? With 1, 2, I can't count this. 3, 4, I'll give it to you. 5 wraps. So I was just about to pull up the holy chart and see where, if anywhere, could they have possibly gotten 5 bifilar wraps from. Middle screen's blaming. I don't know why this is. Oh, I know why it's so big. Here we go. Middle screen.
So generally, the transmission line, the shorter, you've got the right chart there. That's a good one. That's a keeper. The shorter the transmission line, the higher the frequency before it achieves resonance. And you don't want resonance because it crosses over. You want inductance.
All right.
So that Balun, for instance, won't work at 160. It may offer, like, I'm pulling numbers out of the air just to describe it, but it might be 10 or 15 ohms at 160.
Yeah,
which is negligible, but it might present 400 or 500 ohms at 10 meters or 6 meters. And it also depends on the mix of the toroid.
Right. So that's where I was getting into the guessing game of all this. What on earth could it be? And as far as this low turn count, I mean, I love how where's my middle screen? I love how pretty much on these low turn counts, they're pretty much pulling resistive with these low turn counts the entire way, which is I mean, can't be mad there. I mean, you're not getting much of the balancing going on.
Well, resistance, it's equal on both sides. Okay. So it does force a balance.
All right.
What you don't want is where the inductive of the toroid cancels out because of capacitance between each successive winding. Then you have an LC circuit, and it will become resonant at some frequency.
And we see that real often, sometimes in the middle of the HF band around, I say middle, but I see it often happening just somewhere around 10 megahertz, like really often. And I believe that might have something to do with the core material.
Yeah, it depends on exactly how many turns and what is the core material. If you sweep it and you put well, that's a 1-to-1. So if you put a 50 ohm load on the end, you're probably not, it's going to be difficult to see the resonance. You might if you sweep it up at 50 megs, 60 megs, 70 megs.
I'm gonna give it a shot. I've only got the.
It'll look like a dead short.
Hopefully.
Yeah. No, it will. When it's at resonance, it'll be a dead short.
Oh, at resonance. Okay.
Yeah. Right. And that is the top end of that balance. Well, it's way before that actually, but that's worst case. What I would like to know is what have they spray painted the inside of this thing with?
That's it looks like the lawyers made them do it, right?
Yeah, I don't like that, because paint often has a metal component to it.
Right, especially black paint.
Mm-hmm.
Come on, dude, you're killing me. Where?
The good news is I see that they have looks like glass tape around the toroid, so that's good.
All right. I cleaned up in here.
And now you
cleaned up-
can't find anything.
No, I can't find. Yeah, my huge rig expert, right? Like,
Yeah.
mm-hmm. No, I've really done it. Well, let's get
You know, Ziggy, if you put things back where they belong.
Well, I need to know where they belong in the first place. I don't have a belonging zone. I'd really like to have that thing right now. A nice big color screen. That would be the ticket.
Yeah.
Oh, well. I'm going to just rely on this guy. He's all out of whack.
I don't know what I did without, but you know, the days before we had nano VNAs, and I was just
needles.
It's a priceless tool.
Just needles, right?
Yep.
And then even then you didn't know because you were just going by dips.
Mm-hmm.
You'd have to really do stuff. Let's say load. I'm done in RAM. Like right now, I've got a 10 meter on the house right now, but its actual like resonance is around 26 megahertz.
Yeah.
But as far as my radio, yeah, it's not the best antenna in the world. All right, so we're not doing log mag. Let's do. That's my trace. I want to do this and get the swears on it. And we are starting at 1 to 55. I'm going to have to tighten these down so they're not flopping all around. Ooh. See how terrible it is? Did you see it?
I did.
Oh, let me see if I can't get that again. This is some really Bojank stuff I'm doing here. All right, so this could be, it's got to be mostly from that transformer. All right, so we're sitting at 30 megahertz right now. So it's pretty much built for the lower ends, would you say?
Well, first of all, did you calibrate?
I did.
Okay.
Yep. Let's see. I can bypass this, and I have a double here for getting this cable out of the way. I didn't think that we were gonna. There's just dead with the cable.
Right. Good. Good.
All the way across.
Mm-hmm.
And let me go and tell it that this is a load again. And I am done in RAM. Let's see that one more time. Might be liquid tape spray.
Yep, this is good. And then when you're done with that, I'm going to suggest look at it on a Smith chart.
Yeah, we can smith it.
Not that one is any better than the other, just different representations of the same. But it's a different way to look at the map.
Oh, you know what? Oh, let's see. It's not as bad as we thought.
You got a loose connection there somewhere.
Yeah. That's not as bad as we thought. So we are at 1 megahertz here. Of course, me getting close to it's affecting everything.
And comma, that shouldn't. That means you have common mode.
Oh, what? Me getting next to it?
Mm-hmm. If you put your hand there and it moves, that line moves, that's common mode current.
Right, so there's 30 megahertz, and we're sitting at 1.1. And it's almost invisible at the beginning of the HF spectrum. So not bad as far as being out of the way.
So this is
Let's smith it up. Let me get ready to
yeah,
smith.
go ahead.
Yeah, go ahead. I was listening to you.
No, it's all good. It's all good. Because the smith, you'll see if you do a large sweep, you'll see where it crosses over.
Well, I tell you, with these kids, me keeping my own USB-C cable is like
What's
nothing,
wrong with these kids today?
Nothing is sacred, right? Oh boy, I don't know. I've got to have one here. Did you play some radio today?
I sure did. Yeah. It was all good.
Was there a band of choice?
Well, we followed the sun. Started out with 10 and then down to 20 and like that.
How was 10 for you today?
10 was good. 10 was very good, very powerful. You know, I cheat. I use 11 as a marker.
I do it every day.
Because a lot, yep. Because a lot of times nobody's talking on 10, but the band is wide open. But there's always somebody on channel 19 talking. Always.
It's so true.
And if it's 20 over, and I then I go to 38, and I hear 1111111, I know it's time to go to 10. If
Mr. 111 is up, the band's open at least over to Arizona, right? Let's see. I'll tell you something real quick. Hollywood, this is great, right? So on my HS4, my export radio,
right.
I've programmed in the 10 meter and 12 meter steps in the bands with the PC and all that.
Mm-hmm.
I leave it the night before. So before I go to bed, I put it on the FT8 upper sideband. And I leave it at like half volume and half RF gain. And I go to bed. And guess what time I wake up to?
Oh, yeah.
It's about 6 a.m.
Mm-hmm.
consistently.
Wow.
And so I call it my FT8 alarm clock because that's like when I need to wake up.
Sure.
I wake up with the 11 meter or the 10 meter band opening. It's pretty hilarious.
Great minds think alike. I had when I was a kid, I built the crystal radio, as we all did. But I had it feeding into a speaker, and I had a long wire out the window, and I had an AM radio. I think this is probably where the seed was planted. I had an AM radio that was about transmitter, rather, a station that was about 10 miles downrange. And as the sun came up, they would change pattern. And, it was pretty much non-existent, just a whisper in the background. But boy, at 6 a.m. when that sun rose and they flipped the breaker, all of a sudden it would play music, and it would wake me up every morning. Thinking.
I still got you?
Yeah.
Okay. Let's see. I loaded this up. I'm sorry, I missed it. I was having some latency.
I saw that. Yeah,
I think my kids are loading me down.
They're downloading.
No, they're both streaming, probably. Yeah. All right. So, man, I messed everything up. Let's middle screen playing something. All right. Let's connect to a device, maybe. Anything? Nothing? Is that plugged in? Is that plugged in? Everything's plugged in. Let me reset the nano. Rescan. Nothing here. Wait, not a very intuitive piece of software here. Here that are. Oh.
Try again.
I've insulted it.
When in
Must
doubt,
be this
reboot.
wind link slowing me down.
Yeah, you might want to close a few of those windows.
Yeah, this baby's chugging along, right?
Mm-hmm.
Connect to a device. Manage devices. All right. Oh, you don't see anything? Nothing. Well, hit the thumbs up, folks. Is that a 1-1 I gave you today? Lots of 10-meter FT8. All right. It's not seeing it. My computer's not having it. Oh, wow. So Nano VNA Saber is one thing. Ant Scope is another one. I don't know if I can find that. If it's even... Do I have it? I guess is the next question. Because I've always used Nano VNA Saber.
Yeah.
But it's not going to run for me. So we might have to...
Did your computer ding when you plugged it in to the USB? I mean, does it recognize?
I don't know if it would... I don't know how the... I have no idea where the audio is going through. Yeah, we need to figure out if it's,
fair enough.
If it's in manager or not. I have no idea where the audio is. This is the first time I think I've ever done a stream without headphones on, so I'm already in uncharted territory.
Got it. That's what makes it fun.
That looks like my guy Com3, because I don't think I should have anything else. Is my CB radio unplugged? Yes. Yeah. And when I unplug this Nano, does it go away? Uh-oh.
Mm-hmm.
Mm-hmm. So we don't know what that UART bridge is. I bet you it's on this bus, though. I wonder if that's my radio. My 7300.
Unknown device.
I see that. Uh-oh. Incoming. I'm live.
Stop me from breaking stuff.
Hey, guys. You're better than this. Be nice, okay? Please? Okay.
Do nice.
Please be nice. All right, we're gonna bypass the bridge. Going straight in. See, this is why I need to just chuck this VNA. It not only does it do this, but it also randomly locks up. And like I'm starting to explore, like trying to like update the firmware, and I think it might just be.
Except that it runs on its own screen.
It'll do its own thing, like it's like
Yeah.
I've ever wanted it to do. But yeah, now I start asking more of it. Yeah, it's my computer doesn't see it anymore. Let's try another USB cable. That's probably what my deal is.
And then the other thing I would do is shut off. I don't know. It's because I can't see. Maybe you've already done it. I would shut off the VNA, plug it in to the computer, and then turn it on.
Shut up. Yeah. Let's see. What is that? This one? One day, I'm going to make a stream of me going through that big wire bucket back there.
Mm-hmm.
Yeah. I'll be old and gray. It'll never happen. Anything?
For the shortwave listeners, would listen to WTWW, WW. The promo is thousands of volts and miles of wires, and that's what we're looking at.
Let's see. We're charging, but I don't think we're doing data on this either. No data on this one. One
You
more.
cycle the power on the Nano?
Oh yeah, I did. I'll do it again.
Okay. Okay. Just checking because I can't see it.
Oh, good news. I found my rig expert.
magnificent. Do that one.
Yeah. Wait a minute. Oh, but my rig expert doesn't give me a Smith chart, but I can use
Really?
I can use ant scope with it. Yeah, inherently, like on the display, the 35 doesn't give you a Smith chart. Yeah, I just realized that the other day too. I can't believe I didn't ever let that like. I was like, wait a minute, I can't like inherently just see us. No, you can plug it into a computer. They'll let you do that with one of these. Remember these?
Yeah,
the Ds.
yeah. Yeah, my rig expert shows a Smith on the computer screen.
RX. So I get SWR and RNX. All parameters. Oh, sorry. Ziggy, do the thing. There you go.
There you go. Good. That's even better. Yeah.
Isn't it?
Keep it simple.
Yeah, no. Yeah, the 35 zoom, all you get is your resonance and your swirls, and then you get your meter, and then you're all params.
You
Kinda
maybe yeah, I think mine is a 55.
Lackluster.
That's why. Uh-huh.
But I can connect this to here.
Yep.
And I bet you it's probably already found it. If I plug in, they do not put enough.
I would do the RX chart.
Yeah, let's do that. Let's see what it is. Where are we? Surprised it wasn't parked at 11 meters.
I'm not.
All right.
Mm-hmm.
All right, Hollywood. Tell us what we're looking at.
So the X, which is your inductance, well, it's reactance, is going sky high at the top end.
Let's
Interesting.
Let's for giggles.
And it's only showing 10 ohms.
10 ohms across, right? So let's for giggles, let's bypass it. Let me put on my little gender bender and go to the end of this cable that I'm using.
Yeah.
And let's see what the rig expert thinks of just my dummy load here. Just this guy.
Yeah.
One more time.
It should be 50 flat all the way across.
That's what I would expect.
Mm-hmm.
Get a little
55.
bit of
a
little bit of madness
Yep.
On the upper band, but that's because of RF gonna RF. 55 all the way across, right?
Mm-hmm.
Yeah, in the 50s. Let's see. I think it's a little bit better of a sweep.
That's really funky. That should show 50 ohms. Well, I guess it does now. Did you not have the dummy load on it the first?
I've got the dummy load here. This is no dummy load,
right?
Which is what we'd expect. And then this is my very poor attempt at trying to put 50 ohms on this thing. Perfect.
Yeah.
All right. So that's a lot of reactance.
Well, yeah. Okay, so on a 1-to-1, everything looks spot on so far. What you want to do now is look at the common mode, and you do that by putting the rig expert across the Balun, not through the Balun. And it's not going to be pretty because you may have to use some clip leads and that kind of
across the Balun, huh?
Yeah. Like from shield to one side or center pin to the other side, whichever side is hot.
It's not going to be pretty. You're right.
Yeah, you can if you want. If it's not labeled on the two studs, which one is plus and which one is ground, You can just probe it with a voltohm meter.
Oh, okay. You want to find which one do you want to find?
Either.
Okay. I guess we find
And then
one. We find the other.
label it so that you'll know. It doesn't matter. I can hear the peanut gallery. It doesn't matter. It's a Balun. It's balanced. Well, you're right. But it does matter on the phase. If in future you decide to use a couple of verticals and you want one to go up while the other is going down, you need to know the phase of each Balun.
Absolutely.
So
right?
it's a good idea to label them.
Yeah, that'd be like just ganging everything together and not
Yep.
knowing.
Yep. Why doesn't my system work? Yep.
Yeah.
Labels are good.
Let's get some raw wire, I guess. I don't know where I just had it. There's some raw wire. That's perfect. So across. And I need to find my probes. Here they are. I got some new desks today.
Good.
Yeah, they were free today, but they require money in the future.
Mm-hmm.
Yeah. but it's a corner piece and two glass desk. And I thought that those would be those would be a lot easier because I have the desks that have the backs on the back wall, which make cabling just a nightmare.
Oh yeah, yeah.
Okay, so this is my center, left center. And for whatever reason in ham radio, we all do this though.
Mm-hmm.
Yeah. We put DC symbols on AC devices.
Yep. Yep.
All right, so we found center pin. What do you want to measure? You want to measure?
So go from. It doesn't matter. It really doesn't matter. Center pin to that plus or minus. The shield to the -1.
I know what you're talking about. The difference in what happens in between the two is like not even worth talking about. You're talking about the balancing that happens, like just
no. You're looking at the choking impedance now when you do this test.
Okay,
and higher is better.
Let's see. It would be easier if I could just touch it from the outside. I kind of want to know what that is anyway. So there is that. That's tapped. And we want to go. We want to go through it. So we want to send a signal from our analyzer through the outside.
Center pin to the outside, right.
Right. Mm-hmm. And then where do I go here? I need to put a load. I forgot.
Back to the shield of the rig expert at the
but it needs to go through a 50 ohm load though still, right?
No.
Okay.
No,
so
you just want to
out on the return.
Yep.
Down here.
Yep.
Let's do it.
Exactly. Because now you're looking at the choke. You're looking at to see what is the impedance of the choke.
So I would have to screw this in then.
Yeah, I guess you could do that. Yeah.
And we're coming out of.
As long as your red wire on the stud is on the plus stud.
Red wire is now on the plus stud. And then we're just going to short that to ground back here.
Yep.
Okay.
There'll be a little bit of interaction between the two sides, but okay.
You sure we're not supposed to put a load in between there?
No. Because think about it. When you at the end with the studs, there's no load between the studs and the shield of the coax. The load is the Balun. It's stopping the common mode from coming back down the line. And that's what we're looking at now. We're looking at the Balun sideways, not through it.
Okay.
We're going across it.
All right. So starting way down here at.
So way down below the AM broadcast band, it'll look like a dead short.
Over here.
Yep.
With 433 ohms of resistance and an ungodly number for reactance.
Yeah, and I would actually expect that to not be that high resistance. I would expect it to be around 10 ohms because it's just a piece of wire now.
Yeah.
So that tells me that the ferrite that they have used is probably a type 31.
Right, because it happens way down here.
Mm-hmm. Yep.
Okay. I'll agree with that one. And it happens right before the 80 meter band, which is great.
Yep. And where you notice where it crosses over. So it's going from the blue line, which is your impedance. Yeah.
Reactance.
Use your words.
One of them.
So we're not looking at resistance anymore. We're looking at impedance. So this is a reactance, rather. So it starts out inductive. In fact, can you zoom out on the zoom if you hit? Yeah. The scale is, I guess, is what I'm asking for.
Oh,
so it's
I hate the
25
scale.
ohm. Yeah, so it's 25 ohms is the top, and if you zoom out, you'll see that it'll go up to 100 or 2.
Yeah, I mean the resistance right now where I'm at, it's 496 ohms.
Yeah. But where it crosses over, okay, where it goes from inductive to, because inductive is our plus numbers, and minus numbers are capacitive.
I always think of it like this, like the cup for capacitive at the bottom.
Yep. So where it crosses over, that's its first resonance. So that's like the bottom end of where that thing is going to really start working. So it's probably terrible at 160.
Which is sad, right? Because I mean, this is kind of one of the staple things you would use for getting on 160.
Yeah, but there's not enough inductance there. There's not enough turns.
Right. And again, I was talking about.
I mean, if I didn't measure it, okay, just looking at it,
right,
by its size and the number of turns, I would say it's probably designed for 40 meters through 6. That would be my best guess.
All right. So with that guess, we have let's see. Oh, we still got to pull this thing up on the Smith chart still.
Yeah.
Let's see. Let's find a window. This is the Wireman. And he's calling it the 821 Alpha. 821 Alpha. Let's see if that still comes up.
He's going to make a liar out of me, folks.
My God, it says 2 kilowatts.
Oh, no. No. I don't think so.
No. It's got the markings.
It might be 2 kilowatt if the load is already balanced.
I was about to say, you better. Okay. This is not a new antenna, Balun.
Yeah.
Hey, Paul. Frequency range 1.8. Oh man, come on, guys.
Boy, I don't know.
Boy, can you imagine legal limit at 1.8 through this thing?
I have my doubts. I'll leave it at that. Yeah.
All right.
Because the Balun is going to act like, think of it real simple. Think of it as just a huge resistor. In that the power is going out to the antenna on one side, it goes through the air, there's a capacitive coupling, comes back down the other side of because it's a closed circuit, comes back down the other leg of the dipole and returns on the inside of the shield of the coax.
Right.
But it also is on the outside of the shield of the coax. And then the coax becomes part of the dipole. And we don't want that. We want to decouple the coax from the dipole. And that's what the Balun is doing. So if you have, let's say, a 50 ohm dipole, keep it real simple, and 50 ohm coax, and you have a ton of RF coming down the shield, if you put a resistor there on the outside of the shield, it will cut that down. And then it just becomes an Ohm's law equation. And that's what the choke is doing. It's taking that, whatever RF is on the outside of the shield. Remember, coax has 3 wires.
All three conductors.
Yeah. Yeah. And that's a tough thing for a lot of people to wrap their head around until they really see it, you know?
It is a big pill to swallow.
Yep.
Let's see. I saw something that shook me up, and I had to save it. I think I might have already shared it with you. Let's see if I can.
Because the other thing too on 2 kilowatt, if you look at that is enameled wire. So hypothetically, let's pretend that it's no longer a Balun. We're using it not at resonance. We're using it on, let's say, the second harmonic. You know, it's going to be very, very, very high impedance. A couple of thousand ohms. And at full kilowatt or 1500 or even 2 kilowatt that this thing is rated at, I mean, the voltage is going to be, 1 kV just across the enamel. No. If that was PTFE wire, I'd say, okay, you have a fighting chance. But that's enameled wire.
What's arcing? Isn't it like 3K per millimeter? Is that the rule? Something like that.
You're talking about in dry air?
Yeah, there's some kind of slide rule.
Yeah, it's in the ARRL handbook. Or you could Google it. But this is shellacked. This isn't dry air anymore.
You were talking about resistors and putting a resistor against the braid to kind of give the common mode a place to dump to.
No, not to dump to be absorbed and dissipated as heat. And so again, it's 3 wires in the coax. What you've got there, I see the resistor. That's not the correct picture for what I'm talking about. It's
no,
a good
not
picture,
at all. I just found this the other day. I thought it was kind of interesting.
So coax has 3 wires. You want no resistance in the center wire. You want no resistance on the inside of the shield, but you do want high resistance on the outside of the shield. That's what the choke is doing. It's adding that resistance to the outside shield of the coax.
And trying to stay invisible otherwise.
Well, no, it doesn't have to stay invisible. No, because the way it's wired, there is no resistance in series with either the center or the inside layer of the shield.
Right.
It's push pulling. It's sliding against each other.
Right.
But the outside shield is not sliding. It is constant. It is one direction only. And so, I mean, it'll reverse direction with each cycle that you're transmitting. But if you were to take a snapshot in time, you would see the center pin, let's say, going up, the inside of the shield going down with equal value, equal amperage, equal voltage. They cancel each other out. But the outside shield will have its own voltage, its own current, independent of the two. And whatever it has on it will radiate. Anytime you put current, a flowing current on a conductor, it will radiate. And we don't want that. We want to isolate so that it becomes, instead of a 3-wire system, it becomes a 2-wire system. That's what the choke is doing. That's its purpose. Does that help you? Does that make sense?
Oh yeah, no, that's a wonderful way to explain it. It when you
Because
look at it,
if there's
when you look
only two wires,
right,
whatever goes out has to return. If you think, forget about radio for a second. Just think of a flashlight, a battery, and a bulb. The power comes out of the battery, it goes through the bulb, it does some work, it has to return to the source. It has to go back to the battery. And if you were to measure the current going from the battery to the bulb, let's say it's 1 amp, it's a given that it's 1 amp coming back. It's a circle. It's always the same. So those two are the same. So if you have a 3-wire coaxial system, you want the inner conductor and the inside of the shield. Both of those are at 1 amp, let's say, in this example. And we might have a 1/4 of an amp on the outside of the shield. We want to get rid of that. And by doing that, it forces equal current on the two remaining, the center and the inside of the shield. It forces it. That's why it's called a current balun.
now I've always wondered, and probably overthought this at this juncture, right? When we transfer from 3 conductors to, I guess it would be
It's still 3.
this
Yeah.
point. It
Yeah.
would be 3 conductors all the way up until this point,
Yeah.
because you still have the inner and the outer. And so this is where it loads up. This is where it all begins. This is our pure signal that we're trying to retain. And so it's trying to match it here. And then in difference here, it's the core's job to steal it away from here and to balance these two. That's the way I think about it.
I'm going to try to steer you a little bit.
All right.
Okay, so the coax on the right, we know has 3 conductors. We've been through that. Okay, so it has 3 conductors because surface area, the RF rides on a very, very thin area. It's not the thickness of the shield.
No, it's on the skin.
It's on the skin. Okay, so that, if you look inside the balun, that wire that is connected to the shield, it also has surface area. It also has skin effect. So you can't really say that it stops there. It doesn't.
It doesn't.
What it does do is that coil, that wire, is going through the ferrite, and the ferrite is adding an equal amount of inductance to both wires. And because the 2 wires are parallel to each other, they slide against each other. The electrons, as one goes up, the other goes down. It's push-pull.
Yep.
But the total, if I were to short out the 2 posts, the 2 binding posts on the left, and I were to put, this is now, it's common mode now, and I were to put RF through that way and measure it on the shield side of the coax, if that balun wasn't there, it would go directly through. That balun is saying, I'm a choke, I'm a coil of wire, and at DC I'll let you through, but the higher up in frequency that you go, the more inductance I'm going to have, the more resistance I'm going to stop that flow. It breaks the connection.
That's exciting.
It's easier to show than to describe, but
Oh well. No, I think
common mode means it's common to both terminals on the left. It's not one or the other, it's both of equal value. That's common to both sides.
Okay.
That's common mode.
So when we have our what I don't know why I call it, but whenever we have flyback, a standing wave, that's going to create common mode on our shield.
Not necessarily.
Not necessarily. Okay.
No.
I was getting to the common mode exists before on both equally.
The common mode is not. If you put a dummy load in place of that Balun, you're not going to have any common mode. Because it's being dissipated as heat in the Balun. It goes out, it's absorbed, and it flows back through, and everything's hunky-dory. Common mode is caused because of RF. Remember, the signal always tries to find an easy path back to the source. The source is your radio. So you're transmitting, signal is coming out of the antenna, it's going out to Europe, and some of the signal doesn't go through the antenna to Europe. It tries to go into the tree next to it. Some of it tries to go into the ground. Some of it couples into the AC wiring in your building. Some of it goes down the outside of the coax. And that's what the choke is saying, no, stop. You cannot pass.
Let's see. Uh-oh. I hope I don't have a dead USB port. I don't see anything going on anymore. You know, I'm not very impressed with my USB port. I may have an issue. Well, that can't be, because I was rig controlling last night as I was listening to the hoopla.
Yeah. You know what's another good way to think about it?
What's that?
Picture this. I've got 3 rivers. Okay? One is going north. That river's going north, and it feeds into a pond, and then the pond empties into 2 other rivers. Okay?
Okay.
So let's say I have 1,000 gallons going through the first river, and it's dumping into the pond. And I have 2 other rivers, and they happen to be, in this example, equal value, coming out of the pond, going into the valley below. Those 2 rivers, because I got 1,000 gallons going into the pond, and both exit rivers are the same, we can say that each river has 500 gallons flowing, right? Because they're equally sharing it.
Right.
Okay. What happens if I put a dam on one of those 2 rivers? How many gallons do I have on the remaining river then that empties into the valley?
You're going to have an increase in gallons impedance.
How much though? What's the number?
Ooh, would it be half? Half of the total between the 2?
Okay, take a piece of paper and draw it out.
Uh-oh.
It'll help you. It'll help you to picture it.
So we've got.
So you got 1 river,
Uh-huh.
and it's got 1,000 gallons flowing through it. Mm-hmm. Right. Perfect. Great. It goes into a pond or a lake. Yeah. Perfect. And then I've got, on the other side of the lake, I've got 2 smaller rivers. And they happen in this example to be identical.
All right.
So since they're identical, how many gallons is flowing on each river?
It'd be half K each.
Which is how many? You're right.
500.
Yeah, it's 500 gallons. Correct. Exactly right. Okay, go ahead and label that. Great.
And we're all going in the same direction, right?
You betcha.
Okay.
Now let's put a dam. Let's dam up one of those rivers.
Right here?
Yeah. There's a dam there. No water can flow. So the river on the top, how many gallons now must flow through it?
A lot more than it wants to.
Wait, but what's the number?
Be 1K.
Yeah, exactly. You got it. Bingo. That's it. Has to be. Okay.
All
So what your choke, QRM.
One, the one that was on the shelf.
I'll fix it. All right, go ahead.
So what your choke is doing, your choke is the dam on the bottom river. That's the choke. And that forces whatever goes out through the center pin has to return on the inside of the shield. That's the top river. That's the inside of the shield. Whatever goes out has to return the same amount if the choke is there. If the choke is not there, then in this example, this is not a real world example. It's just one I made up. But in this example, without the choke, half of your power is coming back through the inside of the shield, and the other half is on the outside of the shield. Okay.
So by stopping what's going on the shield, we're fixing what's going on the inside.
If you in this example, if you put the dam there, you force the top, and that's the key word. I'm using air quotes, force the current on the top river to be the same as what's going into the system. Because all electricity, it's a circle. It goes around. It has a source. It goes out, it does some work, and then it returns back to the source.
You make it sound so simple.
It is.
It really is.
And I wish I had a chalkboard in front of you I could show you, but and you've done that. This is a good picture. If you're in your car, and I know this is not RF anymore, it's DC, but it might help you to picture it. If you're in your car and you turn the headlights on, you lift the hood, you go to the battery, does it make any difference which terminal of the battery, the negative or the positive? If you disconnect it, the lights go out. It doesn't matter which terminal, right?
Right.
Because the power is leaving the battery, going to the bulb, lighting the bulb. It has to return to the battery. Doesn't matter which wire I cut.
It doesn't want to go anywhere else.
It has to go back to the source. The source is the battery.
Okay.
In RF, the source is your transmitter. It has to go back into the transmitter. And that's a thing that a lot of people get hung up on. They go, well, but it's going out the coax. It leaves the antenna. What do you mean it comes back? Yeah, it does.
Let's see. Is this thing still on? Let's turn this on. I forgot. I've got this neat little, let's see. It should find it. Let's see. I always have, it's so hit or miss with the Bluetooth on here. My daughter's discovered she can see her hand.
Yay.
Where is that 50 ohm dummy load?
So what I just described is not super accurate. What it's just to paint the picture to help you to understand what's going on. Don't take what I said as verbatim. It isn't. I mixed DC with AC and
how dare you?
Yeah. It's just so you get the concept.
Right.
Our radio desks in here.
Yes, I will, honey. Let me finish up with this, okay?
Wait, this lime story.
Huh? Yeah.
And I'll be sharing with you.
Say bye, everybody. Love you.
Bye.
No, at the
Bye-bye.
camera. Here. Sit here. Wave. Wave, wave, wave. They see you. See you right there. Say hi.
Hi.
Okay. And we're back.
And I found this. I found this bag.
You found, hold on.
I found it.
I'm trying to show you guys. Ugh.
See what I found.
What'd you found?
A
You
mark-
found one of my markers.
Yeah.
I was a little shaky there at the beginning. Sorry. All right, here we go. Ta-da!
Excellent.
Hey, like scientists. I'm good with that. That's not terrible, right?
Right.
Kind of a
Right.
almost a
No,
different-
that's exactly what I would expect to see because we're looking at a dummy load. I mean, it's not, just a spot. It has some movement to it as we sweep it. But all dummy loads do. But this chart is not showing us the impedance that the choke is presenting to the common mode flow. What it is showing us is the impedance going into the choke.
Let me set
And
up for that other test again.
Yep.
That's what we were doing.
Yep. We're looking through the choke right now.
Right now.
It's gonna rain.
I know.
Okay, I'll be out in a little bit. Let me check the weather.
What?
I said, let me check the weather real quick.
Alright, let's
I
see.
don't see nothing out there.
I think it's gonna rain.
It might, honey. It's Florida. It rains on a whim. All right. So what did we do? We did.
So we're looking through the choke, Ziggy. So in an ideal world, the choke will be completely transparent. They
and
never are, but in an ideal world, that choke will be completely transparent
And this is
on a one-to-one type.
and just by simply doing this to your center pin, we can easily check.
Let me correct you a little bit.
All right.
Let's take the red wire is fine, but take the let me think
Might
about this
be
here.
this to right.
That center pin.
It's
Yeah,
too easy.
you can leave it this way. It's easier. It's not accurate, but it's close for what we have. It'll show you that it's doing something.
Why did it run well?
You gonna blast out my Sharpie on the ground there? Tear it up, baby.
Ideally, what you want to do is take that red wire,
Ooh.
connect it. That's good. That's actually good. That's showing that it's a high impedance and it's mostly capacitive. And I can tell you it's capacitive because we have it wired incorrectly through the Balun.
Okay.
But the point is that line, if you
Yep.
look at that chart again, it's no longer at the 50 ohm point.
Mm-mm.
It's probably 10 times the 50 ohm point.
Here.
That's a good thing.
Yeah.
Yeah.
So if I'm just guessing at the numbers, looking at the chart, okay, but if that, because it's beyond the 5 and all the way to the right is infinity. So let's keep it simple and let's say that it's 10, not 5, it's 10, because as we go to the right, the numbers get higher and higher and higher. Okay. Let's say it's 10. What does that mean? It means it's 10 times 50 or 500 ohms of choking impedance. So it's as though we've cut the shield. If there were 3 wires, there aren't, but if there were 3 wires, and on the third wire, which is the outside of the shield, we've now put a 500 ohm resistor there in series.
That's a lot of ohms, just saying.
Well, it is, you're right, if on either side of that resistor is 0, then it's a lot of ohms. It's a voltage divider is what we've created.
Okay.
If on the other hand,
HTO.
the impedance without the choke on the outside of the shield, let's say this is why it's important. It's not just what Balun you use, where you place the Balun, the choke. I shouldn't confuse the two. They are synonymous, but let's call it a choke, okay?
Right.
If you place the choke on the coax, where the coax has a high impedance, there's a lot of voltage on the shield, then the choke will have a minimal effect. You're adding 500 ohms to a system, let's say at that point, high voltage, that might have 10,000 ohms. 500 is nothing compared to 10,000. It's going to have less than 1% change. And this is why a lot of people say, oh, that Balun, that's garbage. It doesn't work. It's not the Balun. It's not the choke's fault. It's where it's placed. Chokes have to be placed where the current is high and the voltage is low, because you're adding a resistance.
You put it somewhere where it's all high voltage and there's no stress. It's
going to have minimal impact.
Yeah, it's not going to do a whole lot.
Resistors don't stop. If you look at Ohm's law, you've got voltage and you've got current. A resistor resists current flow. It doesn't resist voltage flow. High current means low impedance. That's where the choke goes. You're adding a resistor there. If you put the choke where the voltage is high, where the impedance is high, it will have negligible effect. So go ahead and take your red wire and touch it to the shield of the rig expert.
So, okay, so we're getting rid of...
right. Now this is correct. So now you're going through sideways through the choke. You're looking at one winding of the choke only. That is correct.
You need me to what, honey? You made me a question block.
Yeah.
Oh.
And here.
Sorry, guys. What you got, honey? Oh, thanks, honey. She made me a little question block.
Excellent.
It's over there. You see it populating?
Yep.
It's creeping up. Is it done? Nope, still going. Still going.
What are you sweeping? What frequencies?
It should be the 1 to 30. Let me see.
Okay.
3 to 30.
Okay, that's fine.
I forgot the. Yeah, 3 to. Oh no, I'm sorry. That's 3 to 8.5. That's awful. Let's start at 1 and let's go to 30.
Yeah, 1 to 30. And you can cut down the number of points. That'll speed things up. If you put that points at 100, that'll speed up the scan.
Yeah, for this we don't need.
Right,
it's gonna be linear.
That's right. That's right.
Hey, and it's different.
Yeah.
Well, we're sweeping a bigger. Hey, look at that.
Mm-hmm.
Kind of go. Here's our phase.
No, do the chart again, because
The
that's
Smith chart?
telling. Yeah, right there. Okay, so look at the blue line, the aqua line. It crosses over the center. You got your hands full.
Oh yeah.
So that blue line is crossing over the equator, if you will.
Go let her
Okay.
out. She gotta go pee. She gotta pee. All right, so yeah,
half of the blue line is above the equator, half of it is below.
Okay.
The part that's above is inductance. The part that's below is capacitance on any Smith chart. Okay. So the fact that it's, halfway, it's pretty much balanced. At some frequency, it becomes inductive. At the other end of the spectrum, it becomes capacitive. That's perfectly normal.
And that's a good split too. That's not a bad, kind of
Correct.
tuning for the middle of the band there. Here's our return loss.
But what's really important about that picture is where on the equator is the blue line. It's way to the right, which is good. It's showing that it has a high resistance value. That's what we're adding to the outside of the shield.
Got it.
That's
So
the
this-
job of the choke. And the further that blue line is to the right, the better. If it were all the way to the right, it would be the ideal choke. If it was at the 5, it would be less effective than the one that you have now. If it was at the 2, it would be even less effective.
I've got another choke on my desk, Hollywood.
There you go. Rock and roll.
This thing's all just freshly wrapped.
Set that up. Give me a minute. I got chicken on the stove. Let me go check it. I'll be right back.
I'll be right here. Let's see. Oh, I forgot to mention the 27 megahertz Marine is all AM mode. Yeah, no, AM is actually for safety reasons, because same as like pilots use AM. Like my picture, guys. They use AM because multiple people can be talking at the same time instead of doing the FM capture where somebody gets trounced. So if this is, I need to test one leg of this and then back to itself. I didn't know that you could do that with an S1. It'd be great if I could lift. That's okay. I can do this. I had that perfect little pin.
Remember I gave you that headlight?
I'm almost done, baby. I promise.
It's the perfect little pen you could use.
I know, honey. This is probably killing you.
That,
Yeah.
see?
We're going to do your hair tonight?
No.
No. You've lost your mind.
Yes. But
I'm back.
All right.
then
So
you can tap on your phone with
one more and we're done, okay, honey?
right?
All right. So, oh wow, I'm sorry. I'm over here dinking around, not realizing what I'm shooting here. It's
all
really
good.
like this is really like more than a one-man job sometimes.
Yeah.
Yep. So I'm gonna feed into the center and I'm gonna pop out and I'm just gonna go back. And we're
Sure.
gonna be measuring the inside, or do you want to measure the outside?
It doesn't matter. That they're going to be the same.
Almost done, okay? Give me a minute. And then we need this device. And I would like to not maybe put my phone on it. I'm sure that's doing something. Let's try to get it just out of the picture. Let's do the test. Hopefully I'm still connected. I doubt it.
In the lab, Ziggy, there'll be a difference between the inner and the outer, but for what we're doing with the Rig Expert, it's not enough to measure. They should be the same.
I did not know that you could do it this way. All right, let's pull the trigger. Boom. I don't know what is going on with my Rig Expert and why it is so working. It has worked every single damn time.
It's because I'm here.
It's you. It hasn't beeped. My phone's not. Everything's worked. Look, multiple scans. There was like we had a little hiatus.
Mm-hmm.
My God. I think one of them auto focusing. This is not fast enough to be on my bench here. That's it. That's all I get. And then of course I could just come to it. So we are further along, but we are capacitive the entire time.
Yeah, but that's okay. It's minimal. It's minimal. It's not down at the -5 or the -2 on the outside perimeter.
But how crazy to think though that this is 10, 11 wraps versus But then again, this is apples and oranges because this is a coax style and this is a bifilar.
Well,
so these are
it's apples and oranges, not so much because of that, but because of the mix of the ferrite. The one on the left, I would guess, is a 240-43.
I think we got 31s.
Okay.
Yep, they're 31s. They sent me a bunch of 31s.
Okay.
Let's, Oh, I need to turn off some of these lines here. Sorry.
Yeah.
There we go. Let's pull it out a little bit. This is the coax one that we just did. Return loss. I like the return loss. Those are good numbers. So I guess the only way to really look at it is on the Smith chart. But this is great because you get all three parameters this way.
That's correct. That's exactly right. That's why the engineers use that first. It's not for everybody, but but I guess what I'm trying to say is don't be afraid of it. I'm not saying you. I'm saying the ham community, a lot of people get all hung up. Oh, it's a Smith chart. It's all confusing. It's a map. It's just a map.
It's a map.
That's all it is. You are here and you want to go there. That's all it is. It's a flat world.
What you got, honey? You're getting good at letters. Almost done, okay? Let's see if I can find. Am I interrupting you with what's on the stove there?
No, we're good. No, we're good. I did steal a little piece of chicken, and it was delish.
I did want to share one more thing, and I want to thank you for hanging out with me.
Yeah.
This is my 8040 fan dipole out in my backyard right now.
Right.
And you can probably help me explain just about how damn near spot on I got this bitch.
Yes, right. Because each of those is where it crosses resonance rather. Those are each leg, one shorter than the other.
Yep. I don't know which one's which though, since this is the beginning. So this is my 80. This is my 80 loop right here on the lower part. Because it's further away, and then this is my 40 loop, and then it just runs on out. Well, I don't know where I started and stopped, so I don't know, to be honest with you. But so I would imagine the broader bandwidth would have been the longer, right? No, yeah.
I would gather that the top circle is the 80.
Okay.
And the reason why I say that is because if you follow that line to the left, it shows, 25 ohms or less, 10 ohms. It arcs up and it goes out of the white, goes to the left where it says 0.5. That would be half of 50. That would be 25 ohms. The center is the bullseye. The one is always 50 ohms. If it's configured that way on the Smith chart, most are for ham radio use.
Yeah. Yes, okay? I was set.
The center is 50. Yeah. You can. I mean, if you're using 600 ohm balanced line, you can make the one equal 600.
Now, hold on. There's something I failed to mention to you. I am using a tuned length of 75 for my impedance transformer.
Mm-hmm.
Yep. So I just hit it at the high, so I know it's a little bit more than 75 ohms out there at the feed point.
Right. Right.
Because I've noticed it's difficult to hit, either the front or back of when you're trying to lower it down. But you don't. Whenever you use coax as an impedance transformer, you'll actually shoot past 75 ohms every time if you're trying to match it to a 50 ohm. Just one of those things. So just prepare for a little bit higher than you wanted. Thanks, honey. I'm almost done. That I think it was the Smith chart, and then I don't know if I showed you any pictures of this thing, but there it is. No choke or anything. Just as raw as it gets with a 75 ohm
And there's
stuff
no
there.
Balun on it or anything, right? At the
Well,
feed
there's
point? Or is there?
there's a choke at the end of this
Down at the
tuned-
bottom.
at the end of this tuned feeder. So this is
Yeah.
still part of the antenna in a way.
Right. And that will radiate some vertical component to the signal.
Right.
Yep.
But for
Which is not necessarily a bad thing. That's
I'm
how
not-
the Carolina Wyndham works.
yeah, I mean for as close as you saw it on the Smith chart that I got it, I'm not mad at it.
Right. Right. Right.
Because I know that most of that power is getting onto those wires.
The power is going to go somewhere. This is all about what's the target? Where do we want to focus the power? Do we want it to just, work, some horizontal, some vertical, some local, some distance? Are we not concerned with that? We just want to talk, it's going to go somewhere. It's all good.
Yeah, it's happening. What did I used to say? It's happening outside of the shack.
Yep.
Yeah.
Exactly. Right.
Alrighty.
And that's a good way to look at it. Yeah, you don't want the RF in the shack where it's not going to do any good. You want it outside.
I've lost all my marbles. Thank you, Hollywood, for hanging out.
Oh,
with
you're
me.
welcome.
I know
You're
you
welcome.
got hot food waiting on you.
Yeah.
Yeah. Let's do it again, man.
Absolutely. Okay.
right.
Have a good night.
Thanks, everybody. Have a good one. See ya.
After this, I want you to get my desk now so I can make you pictures.